All right, here it is. Actually, this isn't really the end, but it's the end of Unit 10, Conditions that Affect Waves. An elastic string's equilibrium length is measured while the string is in a warm laboratory. The string is left outside on a cold winter night. In the morning, the string, while still outside, is measured again, and its equilibrium length is found to have decreased. It shrank. Yes, both things shrink. The string is returned to the laboratory and allowed to warm back up. The string is fixed between 2 points and plucked so that a first order standing wave forms on the string, producing a sound of a certain frequency. Carlos finishes drinking off a bottle of water, then blows across the bottle, noticing that the standing wave that resonates inside the bottle has the same frequency. Wow, that's a crazy coincidence. This must be a TV show. Still fixed to its points, the string and the bottle are again left outside in the cold. In the morning, it is observed that the frequency produced by plucking the string is greater than it was in the morning laboratory, but the frequency produced by blowing across the bottle is lower. Wow, that's crazy. Which of the following wavelengths is the same in the cold outdoors as it was in the warm laboratory? Mark all that are correct. The wavelength of the wave on the string itself, the wavelength of the sound wave in air produced by the air vibrating in the bottle. Huh. We're saying the wavelength is the same, but the note was different because the speed was different. So the wavelength is the wavelength on the string is the same because the wavelength on the string is determined by the length of the string. But I thought the string's length changed. The wavelength of the sound wave in air is determined by the length of the bottle, which didn't change. Okay, that makes sense. The length of the string and boundary conditions didn't change. So we're saying that the string. So the string didn't shrink because it was tied. It was fixed so that it couldn't actually physically shrink, but it could get tighter, right? It's going to try to shrink, so it's going to pull the string tighter. That's why. So there's more tension in the string, and by pulling the string tighter, it's like tuning a guitar. If you're tuning a guitar and you tune the string tighter, the note will go higher. Right. Okay. The wavelength in the bottle cannot change because the length of the bottle didn't change. And here it is. The tension in the string increases. The first experiment. There we go. So I talked about this. The speed of increases because the connection is between the particles is increasing, and information can propagate quicker between the connections. And in air, as it got colder outside, so the air in the bottle is colder, so the speed of the sound wave in air is slower in cold air, and that's why the note was lower, because if the speed decreased, the frequency or pitch had to decrease if the wavelength stayed the same. Wow, we're still going. Explain why the waves on the string are a higher pitch in the cold, but the waves in the bottle are a lower pitch. Okay, so I think I talked about this. Let's look at the bottle. The wavelength remains the same. The bottle is the same. And we know that the speed decreased because it's cold. So the frequency decreased, so that's a lower note. The string has the same wavelength because the length remains the same. The velocity will increase. We know that the wavelength is the same. The speed increased. The pitch has to increase. And there's some notes. Oh my God. Okay, this is the last piece. Cars A and B are identical. The cars are equipped with horns that sound with the same frequency and emit the same amount of sound energy every second. An experiment is performed in which car A is at rest 30 meters from Angela, who's holding a microphone, and B is 10 meters away from Angela, moving directly away from her at 40. Both cars have sounding their horns for enough time that the sound waves have reached Angela before T equals 0. She records data. How fun for her. For a second. So greater than 0 seconds, less than 1 second. So the data taken from the microphone are shown on the graph above. That's some pretty high-end equipment that these kids have, right? Look at that. So the amplitude of the wave varies with time, reaching a maximum minima. This car's horn, so they have the same horn, but one car horn is moving, which will Doppler shift the frequency of it slightly so that it's observed to be at a different pitch than the car horn, which is just sitting there, not moving relative to Angela. And so since the microphone, they appear to have slightly different frequencies, they will constructively and destructively overlap with each other and create a beat frequency. And so we've talked about beat frequency. So basically, there's a lot of writing here. This is all saying the same thing. We've talked about this a couple of times. You can pause the video and read that. And so the difference in the car's horn's perceived frequencies is 20 hertz. That's interesting. I thought that frequencies had to be less than 7 hertz to have beat frequencies. According to this example, they're using 20 hertz. I don't know if that means I'm wrong or they're wrong, but I read it in a book somewhere that it had to be 7 hertz difference, otherwise you didn't get a beat frequency. So it's possible that Often Wrong Workbook has done it again, but it could be that that perhaps needs more research. Why does the amplitude decrease over time? Because the car's moving away and it's getting less, as it moves away, the sound isn't as loud. When things go away from you, they're not as loud. What's happening here? That's it. Now, next week, we'll be looking at these review questions. 11 review questions. That's what we're working on. So we're basically going to level up and do side quests. Thank you.